I'm honored to have you here, so sit back, relax, and enjoy the show. Welcome aboard as we set sail on a journey through diffusion-controlled reaction. Diffusion-controlled or diffusion-limited reactions are reactions in which the reaction rate is equal to the rate of transport of the reactants through the reaction medium, usually a solution. The process of chemical reaction can be considered as involving the diffusion of reactants until they encounter each other in the right stoichiometry and form an activated complex which can form the product species. The observed rate of chemical reactions is, generally speaking, the rate of the slowest or rate-determining step. In diffusion-controlled reactions, the formation of products from the activated complex is much faster than the diffusion of reactants, and thus the rate is governed by collision frequency. Diffusion control is rare in the gas phase, where rates of diffusion of molecules are generally very high. Diffusion control is more likely in solution, where diffusion of reactants is slow due to the greater number of collisions with solvent molecules. Reactions where the activated complex forms easily and the products form rapidly are most likely to be limited by diffusion control. Examples are those involving catalysis and enzymatic reactions. Heterogeneous reactions where reactants are in different phases are also candidates for diffusion control. One classical test for diffusion control of a heterogeneous reaction is to observe whether the rate of reaction is affected by stirring or agitation. If so, then the reaction is almost certainly diffusion-controlled under those conditions. Let's now shift gears and explore derivation through a critical lens, uncovering its strengths and weaknesses. The following derivation is adapted from Foundations of Chemical Kinetics. This derivation assumes the reaction a BC. Consider a sphere of radius r centered at a spherical molecule A, with reactant B flowing in and out of it. A reaction is considered to occur if molecules A and B touch, that is, when the distance between the two molecules is RAB apart. If we assume a local steady state, then the rate at which B reaches RAB is the limiting factor and balances the reaction. Therefore, the steady state condition becomes 1. KRB, where JB is the flux of B, as given by Fick's law of diffusion. 2. JB equal dAb frac bedrau frac cup frac duja, where dAb is the diffusion coefficient and can be obtained by the Stokes-Einstein equation, and the second term is the gradient of the chemical potential with respect to position. Note that refers to the average concentration of B in the solution, while R is the local concentration of B at position R. Inserting 2 into 1 results in 3. KRP redia frac bid fracka frac duja. It is convenient at this point to use the identity ix bookup dot frac ix bookup equal a frac bid fracka frac duja, allowing us to rewrite 3 as 4. KRP redia bix bookup dot frac ix bookup. Rearranging 4 allows us to write 5. A frac x bookup terpi redia frac ix bookup. Using the boundary conditions that are the local concentration of B approaches that of the solution at large distances, and consequently at 0, as R, we can solve 5 by separation of variables. We get 6. Int R by infti frac x bookup terpi dia bint R by infti d rix bookup, or 7. A frac p dia beta R bex bookup, where beta int R by infti frac rix frac hook beta. For the reaction between A and B, there is an inherent reaction constant Kr, so R a big Kr. Substituting this into 7 and rearranging yields 8. Kr frac p dia beta Kr plus A p dia beta x frac warp bt. Now, let's delve into the intricacies of very fast intrinsic reaction and explore its various aspects. Suppose Kr is very large compared to the diffusion process, so A and B react immediately. This is the classic diffusion-limited reaction, and the corresponding diffusion-limited rate constant can be obtained from 8 as kdub. 8 can then be rewritten as the diffusion influence rate constant as 9. Ik frac dk r plus k dex frac bt. Now, we shift our focus to weak intermolecular forces, a topic that deserves our attention. If the forces that bind A and B together are weak, yeah 0 for all R except very small r, beta approx frac ab. The reaction rate 9 simplifies even further to 10 Kr frac dk R plus Kd. This equation is true for a very large proportion of industrially relevant reactions in solution. Let's now turn our attention to viscosity dependence and examine its role within the larger context. The Stokes-Einstein equation describes a frictional force on a sphere of diameter r as dr frac pra, where is the viscosity of the solution. Inserting this into 9 gives an estimate for Kd as r frac where r is the gas constant, and is given in centipoise. For the following molecules, an estimate for Kd is given. Solvent viscosity centipoise Kd frat times em.s and pentane 0.2427 hexadecane 3.341.9 methanol 0.5511.8 water 0.897.42 taurine 0.5911. Solvents and Kd. Share this video with your friends and spread the knowledge.